First, a little bit about my background. I grew up in Basel, Switzerland, where I attended the Mathematisch-Naturwissenschaftliche Gymnasium, which is a high school with an emphasis on math and science. And during my university years, I then took lectures in mathematics in this 500-year-old building. And before me, in that very same building, there were some famous people like Jacob Bernoulli and Leonhard Euler. So somehow math and geometry got into my blood very early on. And then in high school, I fell in love with geometry. And in the 11th grade, we had a subject called descriptive geometry. And there we tried to construct, things with circle compasses and rulers that are like intersections between cones and cylinders and the like. And I really thought that was utterly cool stuff. So ever since, whatever job I had, I was always looking for the geometry component. And fortunately, over the last 40 years of my career, I had a fortunate fate of being associated with many, many interesting and challenging projects that all had a strong geometry component. So in the top left there, you can see the first solid-state television camera built on charge-coupled device technology. That was built in our group at Bell Labs. Then I came to Berkeley. I teamed up with David Patterson, and our students built the first reduced instruction set computer on a single chip, shown on the bottom left. Then computer science needed a new building, and suddenly my geometry went from 2 dimensions, laying out chips, to 3 dimensions. And I was heavily involved with Sutardja Dai Hall, and some of my star students, Seth Teller and Tom Funkhauser, created the first interactive walkthrough program with which we could walk through Sutardja Dai Hall before it was even built. And some of the techniques that they developed in that context are still being used when you're playing Dungeons and Dragons or any other video games today. And then in the late 90s, I started to team up with Paul Wright and Dornfeld and others in mechanical engineering, and we started to build all kind of mechanical gadgets and the calculating tool paths to machine those gadgets. But then, in the last 15 years, I started to team up with artists and with mathematicians. And here are some of the results. And that's a little bit what I'm going to talk about today. Let's start with some very simple geometry. These are the 5 Platonic solids. They're very beautiful, simple geometrical objects. And these regular polyhedra were already known to the ancient Greeks. They thought that they represented the 4 elements found in nature: air, earth, fire, and water. And then the 5th one would represent the overall structure of the universe. And these 5 objects have played an important role all throughout the last 2,000 years. For instance, they played an important role in Kepler's life. After Kepler had found the motions that control the speed of the planets in their orbits, he then tried to find an equally simple law that would tell us what the sizes of these various orbits are. And one thing he tried is to take the first polygons, triangles, square, regular pentagons, and draw the inner circles and outer circles and see whether that would give the right ratios of the distances between the planets. Well, that one didn't work. And then he had this inspiration, because at that time there were exactly 6 planets were known, and there were 5 Platonic solids. So, using the 5 Platonic solids with their corresponding inside spheres and outside spheres would be a perfect way of getting the scales for all 6 planetary orbits. Unfortunately, it didn't quite work. And many years of his life, he fudged it, and he said, well, if there's the moon, we have to take the orbit of the moon into account to make that shell thick enough so the moon would fit in there as well, and so on. And he got closer and closer and closer. And then, unfortunately, they discovered one more planet, and the whole thing was on. It also played an important role in architecture. And if you look at the Buckminster-Fuller domes, they're primarily based on icosahedra and then truncated icosahedra and so higher order versions of subdivisions of the icosahedron. And most recently, we find that these structures also play a role at the atomic level, and we know about buckyballs, and then we know very similar connections between atoms that form these carbon nanotubes. And before too long, it will lead to some kind of molecular manufacturing where we can build miniature struts and lattices from these building blocks. And some of the schemes that people are starting to think about start to look really kind of complicated, but also kind of attractive. And you can see this could already be kind of a sculpture in its own very right. I mean, it's at least as good as the Coke bottle sculptures that you find in AT&T Park. So you can really see the connection here between geometry and science and art. A few years ago, we were fortunate enough to have Dr. Ivan Sutherland as a visiting professor in our department, and his office was right next to mine. And he's typically considered the father of computer graphics, and we had many good discussions. At some point, when I was preparing a similar talk to the one I'm giving here, he asked me this question: Carlo, what do you think? What came first, art or mathematics? Who thinks art came first? Who thinks mathematics came first? All right, here is some very old art, dating back, about 40,000 years, about 25,000 years. I don't think that this needs any mathematics. I think mathematics started to come in when humans started to build regular things, when they tried to fit ornaments that go around the basket or a vase, or some pattern that fit around a column, or some cupola. Now, mathematics was clearly required, okay? But probably that came at a later time. But then I thought of a different question. What came first, art or science? Who thinks art came first? Who thinks science came first? Okay, well, how can we figure this out? I think we first have to figure out what is it that we call art, what is it that artists are doing, and what are scientists doing? So let's ponder these questions for a moment. I think that the role of scientists is primarily they're model builders. Okay? They very carefully observe their environment, their domain of interest, and then they cast their findings in a predictive model, which they may refine over time. Okay? That model is simplified view of what they see in nature, it's abstracted, and the most important thing is that it has the quality that you can change some parameters and then predict what would happen in nature if you do the same thing. What is it that artists are doing? I think artists also start with observations of the world. And then they render that world, again, from a very special point of view, maybe their own perspective, maybe they want to emphasize some aspect of what they show of the world to make a statement or change some policy, or maybe just project an ultimate vision of a more ideal world or a more dangerous world. But I think in both cases, we have something in common, and that is that we have intense observation and study, which is then followed by some selective, abstracted documentation. And so perhaps there is a common origin between science and art, and perhaps both of them really have evolved in parallel. Here is a pair of sculptures, which is inspired by a phenomenon in nature. When high energy particles from the sun hit the Earth's ionosphere, then wonderful light displays can result near the northern pole, and there they are known as aurora borealis, or near the southern pole, where they're known as aurora australis. And often these northern lights look like sort of undulating curtains or ribbons, and it was the image on the upper left and some other images like it that inspired me to make the two sculptures that you see here. From a mathematical or geometrical point of view, both of these are Mobius bands. Okay? And the interesting thing is that at the bottom, the Mobius band is curved, and then it swings around and it meets itself again. But you know, a Mobius band comes back upside down. So how can that be? Well, because on top, the band essentially goes flat, and so it could do that inversion and make that closure possible, even though the cross-section is not flat here at the bottom. This sculpture is inspired by knot theory. This bronze sculpture is about 16 inches tall. It presents an artistic rendering of the torus knot shown at right. A torus knot of type P, Q is some string that winds around an invisible donut, and it goes P times around the big circle, around the hole, and then Q times through the hole. And then by using a somewhat more angular shape for the torus and a more interesting cross-section than just kind of a round chord, I was able to turn essentially a simple mathematical knot into an artistic kind of rendering. And here is a small wood sculpture done by Brent Collins. He is an intuitive wood sculpture artist living in Gower, Missouri, out in the boondocks, half an hour north of Kansas City. And many of his sculptures have been inspired by nicely balanced saddle surfaces. These surfaces are known as minimal surfaces, and they're the kind of shape that you find in soap bubbles. If you take an arbitrary crooked wire and you dip it in soap film, you pull it out, the shapes that you have in there are exactly of that kind, nicely balanced in both directions, because any small change in the surface would actually increase the area of the surface and therefore increase the energy, and nature likes to go to the lowest energy state. So this object, which Brent Collins called the hyperbolic hexagon, prompted me to pick up the phone and make contact with Brent Collins, and it started a 19-year collaboration. As mentioned, it started with the sculpture on the left, the hyperbolic hexagon, and then in the middle you see Brent Collins holding our first truly collaborative piece, which was finished 2 years later in 1996. And it's sort of in the same family, but it's somewhat more complicated. And then to the right, you find a shape that we called heptoroid, another 2 years later. And now this is even more complicated, because there's clearly something twisted in there that you didn't see before. So let's focus on the shape on the left. Even though Brent Collins had no formal training in mathematics whatsoever, these shapes have a very distinct and direct connections to mathematics. In particular, the hyperbolic hexagon on the left can be understood as a 6-story shirk tower wound up into a loop. Let me explain. On the left is a picture of Shirk's second minimal surface, which he discovered in 1834. It's one of those minimal surfaces that could be taken on by a soap film. It consists basically of 2 planes crossing themselves in the z-axis and then going off to infinity. That's kind of boring out there. But where they cross, there's a sequence of holes and saddles stacked along the z-axis, and this is the interesting part for a sculpture. So we cut away the large boring flanges and give the middle part there some thickness so it becomes physical, and that's what I call a shirk tower. On the right you can see a generalization. We can use higher order versions of the shirk surface. That's when you get, say, 4 planes crossing at the z-axis, you get these higher order 4-way saddles. So, on the left you again see the shirk tower, and in the simplest case it's composed out of very simple biped saddle, the kind of saddle you would find on the back of a horse. If you had 3 planes crossing, you get the so-called monkey saddle. The monkey saddle has 3 grooves down, 1 more for the tail, okay? And then 3 ridges going up in between. And by stacking 5 of those monkey saddles, you can make some interesting sculpture. And then here is sort of a model of this particular thing, which is just rendered as a virtual image in this particular image. But then we can also take this shirk tower and bend it into a loop. Okay? Before we bend it, we can either give it a twist or not. If we just take a straight 4-story tower and we do not give it a twist, the result would be what you see on top. It's very symmetrical, but it's kind of boring. Okay? If, on the other hand, we take that same structure and we twist it by 180 degrees and then join the 2 ends, then you get the structure down here. less symmetrical, but I think it has much more dynamic energy. In my very first phone conversation with Brent Collins, which lasted about 45 minutes, we talked about all of those things. And in particular, we realized that if we had an odd number of stories in that shared tower, you have one more story, then you would get something like a Mobius surface. Okay? Because right now, the bottom surface here is green, and the top sample is green. So you bring them together, green meets green. If you had one more story, then the top story would be yellow, and if you bend it and bring it together, yellow meets green, and now you suddenly have a single-sided or Mobius kind of surface. Also, if you give it a twist, then what before were 4 separate contours for the edges, suddenly now edge number 1 after one loop would go in edge number 2 and 2 into 3 and so on, and they may form complicated knotted structures. And this all sounded really, really very intriguing, but the question is, does it lead to any good sculptures? That was not clear, and it's very hard to imagine that, when you wave your hands on the phone and your partner cannot see what you're saying. So, computer to the rescue, to explore all these possibilities, I wrote a very special purpose computer program, and the only thing that this program could do was make these kind of shared towers. But I could control the number of saddles, the order of the saddles, the width of the flanges, the thickness of the flanges, whether I bent it into an arc, whether I bent it into a loop. And by just moving these sliders around in real time, I could see all of those shapes. And so literally, in a matter of minutes, I have all these possible shapes popping out of this program, which I somewhat pompously called Sculpture Generator number 1. So, all of these are basically just the twisted toroids coming out of a shared surface. And then some of them we actually built. This more complicated thing, which was on the right-hand side of that earlier slide, we called the heptoroid, because it had 7 stories. Each of the stories a 4-way saddle. It had some twist in it, and because it was 7 stories, it was a single-sided surface. So it's a pretty intriguing, wonderful sculpture. It was exhibited at the Fermi Lab, and everybody there, all the physicists, they saw something different. Some of them said, oh, it's just like a stellarator. And others said, no, it's like the head of a boring machine that we use to drill our tunnels. And somebody else said, no, that's the structure of a quark. So, it's pretty cool to have these objects, but every sculptor dreams of having really large sculptures. I mean, large is always better when it comes to sculptures. And so, indeed, we got the chance of building a 12-foot tall sculpture. However, it was constructed of snow. And this actually happened at the annual sculpting championship in Breckenridge, Colorado in January 2003. For obvious reasons, we called our piece the World Wide Web. And the jury really loved it. They thought it was so 21st century, it was wonderful and all that. And as you can see, it turned out rather nicely. And it was still looking good at 12:40. But when this woman took her photograph, it sounded like whoosh. And at 12:41, that's what the sculpture looked like. And you can see the temperature at that time was 42, which is not very good, even though it was January, 3,000 meters, Breckenridge, Colorado. Fortunately, the jury had ended at noon, and the jury stuck by their decision, and the World Wide Web was awarded the silver medals. And we stood there with our little model, and we told everybody, believe me, it was really beautiful. So, it was heartbreaking. They can see why I now tend to rely on more solid substances. And so the second collaborative piece with Brent Collins, the hyperbolic hexagon number 2, which you see here, was actually cast from the piece that he carved in wood in bronze. And one of the copies that was cast from it, you can actually see in Sutardja Dai Hall. If you go into the 3rd floor lobby and you go to the little ante-room, which has glass doors, fortunately, that goes into the director's office, you can see it standing in there. So, what I've shown you so far clearly exemplifies what happens when art is kind of the initial lead, the initial inspiration. I then apply mathematics, in particular computer science programs, to capture the essence of that art, and then I can use that, produce more art. And among the shapes that came out of that sculpture generator, here is another one. You can see its specifications on the right. The branches are fourth order. It has 11 stories, 12 stories including going through the black pedestal there, and so all the parameters are listed. And for me, I would like to call this the solar circle, because there's a clear correspondence for me to the 12 houses in the sign of the zodiac. And we also got a chance of building this one at a scale of about 9 or 10 feet, thanks to the help of this man, David Lynn, from Nova Blue Studio Arts in Missouri. And there was a local art center, actually not an art center, it's a community center. It has some art stuff, it has a gym there and all of that. And in their atrium, they wanted this particular sculpture magnified about 10 feet across. They wanted a lightweight indoor sculpture, possibly translucent. And David Lynn cast this sculpture in polyester resin. This is quite an elaborate multi-phase process, and in the following we'll give you kind of a glimpse what it took to build this particular structure. So first we had to define the actual master module, and you can see it here. It's 1/6 of the whole sculpture, and that element is essentially then repeated 6 times. And this original piece was carved on a numerically controlled milling machine out of high density styrofoam, and then it was coated with clay to make a really nice smooth surface. And then on that master module, David now created a mold, and the mold was essentially a layer of silicone rubber and then a layer of fiberglass and epoxy to make these plates. And then in that mold, which I think for this particular object had like 20 separate parts, he then cast the actual pieces that we needed in this polyester resin, and he had to make 6 copies of that. Then the copies were fused together, and here we see the final assembly stage. There are 2 hemicircles, both of them have 3 of those stages. We're now at the bottom of the atrium where it's going to be hung, and then another 24 hours were needed to essentially pull the 2 halves together, fuse them together with epoxy, and then apply some heat in order to cure it. And then 24 hours later, when it was really hard and solid, then it could be lifted up into its place. Here again you see on the left Brent Collins, and on the right the man who built this thing, David Lynn. This is what it looks like at night, seen from below against the atrium. Our customers wanted to call it Millennium Arch. That was fine with me, as long as they paid the bill. But it prompted us to also take this particular photograph. And, Brent there as the Millennium Man, in a sort of deference to the famous Vitruvian Man painting by Leonardo. More recently, as a matter of fact, about a year ago, we got an opportunity of building another one of these kind of sculptures for Missouri Western State University. And Brent and I decided to really go out on a limb and build something kind of wild. We thought we might try to take these whole saddle chain that you find in the Shirk Tower and take like 24 of those stories and wind them along a space curve that would form a trefoil knot. On the right is the first quick mock-up, which I proposed on a computer and showed it to Brent and says, "Do you like that? Shall I pursue it?" And he said, yeah, that looks cool. Let's try to go for it. And we decided to call this Evolving Trefoil, because really the name sort of implies or reflects the fact that the concept came out of a lengthy evolution of ideas and forms, starting all the way with the very simple Shirk Tower on the left and then progressing through ever more complicated structures. The only problem was that my sculpture generator could not do that. It was not built to do that. But fortunately, we have some smart graduate students and undergraduate students, and with the help of QSIM, I modified my sculpture generator so the Shirk Tower could not just be bent along a circular arc, but could actually be swept along an arbitrary space curve. And you see a first design here kind of popping up in the sculpture generator number 2. I then used that file. I went to a rapid prototyping machine and made a maquette. And then on the maquette, I found some flaws, some ways to improve it. And eventually we got to a more refined design. When I thought I really had it, to be absolutely sure, I went again back to the rapid prototyping machine. And I really built those master modules that we would need for this particular object. What you see here is about the build process halfway through. The actual sculpture is kind of the yellowish stuff. The white stuff is really just scaffolding to hold up the plastic at the right place until the whole sculpture was finished. If you bring these parts out and then you wash away all the scaffolding, well, that's what the modules look like. And then 6 of those modules would make the whole sculpture. So I started to assemble them and see that they really go together. And I also shipped those parts to David Lynn. So he knew what was coming and he could figure out how eventually all of these things had to come together. Now for the real thing, this is a much more complicated structure than Millennium Arch. It again starts with a master geometry that's milled from high density foam and then coated with a brown clay stuff. And the whole piece then already weighed about 40 or 50 pounds. Then a mold is formed around it, involving again silicon rubber and then fiberglass. And the form was so complicated that they kind of color coded the various shells, so they knew actually how it would go together. Then each of the mold pieces essentially has, an inner layer which is silicone rubber, and that's the one that captures the very fine details of the surface, makes sure it's nice and smooth. It's the pink stuff. And then layers of fiberglass, held together with epoxy. That's making the blue shelf to give the whole thing some rigidity in the local domain. And then to make the whole thing rigid overall, there's essentially this armature of rebar that keeps the whole structure to make it really rigid and maintain its form. Because in the end, the form better be exactly what it is, or the 6 pieces wouldn't go together. Now, once you have this form, which, again, breaks apart in multiple pieces, you then build on each one of those forms on the inside layers of fiberglass held together with epoxy to make essentially a shell that would eventually be the wall thickness of the hollow thing you're building. And then each of the part has its own shell built on the inside. Then you bolt all the various parts together. And at this point you have a hollow shell that already essentially has a crude wall out of fiberglass. Now you fill the whole thing with some kind of catalyzed matrix, which is filling the whole volume. It's kind of a viscous syrup of epoxy resins and crushed minerals blended together with some catalyst. And now the whole assembly with the catalyst and matrix inside is about 300 pounds. And the thing has to be essentially rocked back and forth and rotated so that the syrup really goes in all the nooks and crannies and covers the whole surface and all the joints and everything like that, and makes a piece that really has a nice and smooth surface. And he had to do that 6 times. I understand he actually had to try 8 times to get 6 good ones, because sometimes you just miss something and there's some cracks or something that's not nicely covered. Here are 3 units essentially assembled, tentatively, because he couldn't transport them if they're all glued together, in his studio. And then a few days later, basically 6 of those units. And then finally the whole thing got shipped and again assembled at the bottom of the atrium in Missouri Western State University, and pulled up to the atrium of Angenstein Hall, which is the science building in Missouri Western State University. And it's really a fantastic place for that sculpture, because it's a 3-story atrium. You can see it from below, from eye level, from above, and from every direction it really offers a different view. Again, there's kind of a close connection between that shape, and I have sort of several associations between the evolving trefoil. The trefoil, of course, represents mathematics. But then we have these almost minimal surfaces, and that's clearly soap films, physics, chemistry. The twisted nature of it, kind of this twisted thing, that's like a helical strand, that could reflect, biology. And then the bone-colored surface that we got for the particular plastic and polyester that they used, to me that may be like a bone structure, so there is paleontology. Now, the evolution per se, and particularly in Missouri, it was important to stress evolution. You know, it has something to do with life sciences. It's a theory, but it's a good one. And then finally, it's really an elaborate truss structure, you know, and so that's where engineering comes in. Another thing to celebrate engineering started with yet another shape that came out of the sculpture generator and was done on a fused deposition modeling machine. This little piece I sent off to Dingley, China. Okay. Dingley, China is a shop where they take models and they carve them in stone. It's the same place where they also carved the Martin Luther King Memorial in Washington. You didn't know that was made in China? Basically, they sent them a plaster model and says, make it 20 times bigger. And they essentially carved, you know, I don't know, have 20 or 30 3-foot by 3-foot by 3-foot blocks, you know, shipped in separate containers, and then they all stacked them together the right way. There is Martin Luther King looking out over the Washington Mall. Well, in my case, I sent it off. I didn't hear anything for 3 months, and then they sent me a couple of photographs, essentially telling me it's coming along nicely, and I was kind of comparing it, you know, to the shape that conceptually I had in my computer in mind. And then just a few days before they created it up, they essentially sent me this photograph. It says, it's coming. And I was really thrilled. And indeed, a few weeks later, you know, a shipping container arrived essentially in Oakland with 2 boxes, and here they are. And when we ripped them open, that's what we found inside. And a few hours later, we had it installed, and it's standing on the 6th floor terrace behind Sutardja Dai Hall, between, you know, Davis Hall and Sutardja Dai Hall. So normal office hours, you can readily go there and actually touch it, and, you know, sculptures are meant to be touched. And when you look at it, you just realize it's not only an elegant form, but it's also incredibly beautiful craftsmanship. I mean, I couldn't believe, you know, just how cleanly everything is. There's no nooks and crannies. I mean, it's all one clean shape. You know, you run your hand over it, and it's totally amazing, you know, and all the details. So I just wonder how many Chinese children for how many hours sat there with, you know, this little gritty paper there and try to make it. Anyhow, check it out on the 6th floor of Sutardja Dai Hall. Now, in the second half of my talk, I really want to talk about math to art. I want to talk about something that starts essentially with pure math and was aimed to make visualization models, but some of them are beautiful enough that I think they could also serve as sculptures in their own right. And then sometimes I embellish them to the point, so to make sure that I felt that they could become sculptures. Who knows what a Mobius band is? I would think most of you probably have seen something like that. Okay. The single-sided Mobius band that you get when you take a belt, but rather than closing it straight, you give it a 180-degree twist. It becomes then single-sided or non-orientable. And whenever we find red and green essentially coming against one another, that means you can no longer distinguish one side from the other, because you can readily go from red to green. It's then single-sided. Now, this surface has only a single edge, and that can see a little bit more clearly in this static image where I have highlighted the edge in yellow. It sort of makes a double loop, or roughly a folded up figure-8 shape. But that's not the only shape for a Mobius band. Mobius bands can come in many different forms. For instance, it can come in this triply twisted form, which you see in some of the recycling symbols. Not all of them are triply twisted. You know, they're kind of bad ones that are only singly twisted, not perfectly symmetrical. But we can now deform this particular Mobius band in many different shapes. And here are just some simple changes that we made by deforming the band itself, but essentially keeping its width. And to a topologist, it's okay to have surfaces pass right through one another, and that's why the third state is still perfectly legal. And you can see that artists all over the world have really used all of these shapes of Mobius bands. So the leftmost form you may find in some wedding bands. Okay. The second form was celebrated by Max Bill, and it's the form that somehow seems the least twisted. Wherever you go, it seems the ribbon is just bending, not really twisting. And then M.C. Escher has celebrated both states on the right, the one that has a self-intersection and forms a perfect figure-8, as well as the triply twisted state, which we found in the recycling symbol. Okay. But there are also ways in which we can deform the Mobius band so that this figure-8 loop of its rim becomes a perfect circle. On the left, you see a shape that's known as the Sudanese Mobius band, which was discovered by Sue Goldman and Dan Asimov, not in the Sudan. And on the right is a configuration known as Boy's cap. It has nice threefold symmetry, but it has now self-intersections, which is of good or bad, depending on what you want to do with it. We will use this part later as a building block for more complicated surfaces. Now, you may find it really mind-stretching. How can a Mobius band be deformed into this Boy cap shape? Well, maybe these figures help a little bit. They show that transformation. We start at the top left with a triply twisted Mobius band, okay? And then we gradually broaden the band, so it starts to infringe on itself in the middle. It forms kind of a triple intersection point, but we let it grow in further. Okay? The band then goes through itself and eventually becomes a shape that is one of these Boy's cap that has just a tiny little circle missing, and that's the circular ring. So, all of the shapes you've seen so far are basically single-sided, and all of them have one ring, okay? One boundary. That's a Mobius band. Are there any single-sided surfaces that have no boundaries? Anybody heard of a Klein bottle? Yes. So there now we have a shape that is also single-sided, but there is no boundary. Okay? It has a self-intersection. Here essentially, that hose goes through the wall. Topologists don't worry about it. It's not a fixed connection. You're not allowed to step from one surface onto the other one. Okay? And in order to convince you that this is really sort of a single-sided surface, I've singled out one small ribbon, which I've colored sort of in orange and green, and I have these walking normal vectors on top of it, and you can see they're kind of diving on the inside, and then they're coming to the outside, and sometimes they're inside the handle, and then on the next pass, they're on the outside of the handle. Okay? So clearly, there is no distinction between inside and outside. You can go from one side to the other side without stepping over an edge or without having to drill through the surface itself. Again, there are many different forms of Klein bottles. All of these are variations of this very classical Klein bottle geometry, which I call sort of the inverted sock, because at the end it looks like, the inverted sock after you wash them, put them away in your dresser. Okay? At the very left, we have maybe the largest Klein bottle ever made. It was made by Cliff Stoll, living right here in Berkeley. And if you go onto the web and look for Acme, A-C-M-E, Klein bottles, you find a wide assortment of Klein bottles that you can purchase there, and a lot of funky pictures. The right two images are basically the same kind of Klein bottle, but now the handle is not just making one loop and diving inside. No, it makes a triple loop in the middle, and it goes inside and makes this whole spiral that looks like a distillation column, that we use in the chemistry department. But topologically, they're still exactly the same. They're basically this bulb with a handle that sticks through the side and then converts in an inside-out manner at the mouth of the Klein bottle. So what is the essence that makes a surface a Klein bottle? Well, here is a constructive recipe. Start with a rectangular domain as shown on the top right, and first we join the top and bottom edges marked by the green arrows, and they point in the same direction, so we can just roll this thing up into a cylinder as shown at number 2. Now we have to join the other two edges, but they, if you look at the markings with the brown arrows and at the labeling, they actually are in the reverse direction. So somehow we have to make a twist, and that of course is what will make it a single-sided surface. How can we do that? The labels certainly don't nicely line up when you look up there. But if we take the left end and we narrow it down, and we take the right end and we fatten it somewhat, and then we stick the left end through the side and line it up here, then you find that on the inner ring and the outer ring, the labels are perfectly lined up. And so now we can just take the inner surface, invert it like a sock, smoothly connect it to the outside, and voila, we got ourselves a Klein bottle. So having that rectangular domain and making the connection as indicated by the green and brown arrows, that is all it takes for a topologist to define what a Klein bottle is. Okay. But I claim this is also a Klein bottle. Okay. What is this thing? So it looks like a tube with a figure 8 profile that forms a ring and then is kind of twisted together. How can that be a Klein bottle? Let's go back to a recipe. Okay. When we merge those two horizontal edges, the green arrows, we just need to bring them together. But nobody tells us to just make one round tube. We can make a figure 8 connection. Okay? So that's a perfectly good connection to bring the two green arrows together. Now if you look at the labeling, what has happened? Well, the 2, for instance, up on the top on that side, and it's a bottom down here. Okay, 6 and 7 are down there, 6 and 7 are up here. So what should we do? Well, we take this figure 8 configuration and we essentially twist it through 180 degree and merge it. Okay? So, with a 180 degree twist, we can bring the two ends together and then we fuse them and we find out that all the labels match up perfectly and we get the shape that you see at the bottom right. Actually, we can do this twist right-handed or left-handed, and that will lead to 2 different Klein bottles. At first glance, they kind of look the same, but really there's a right-handed version, left-handed version. They're mirror images of one another. And there's no smooth transformation that will take one of those Klein bottles and transform it into the other one, or, for that matter, into the inverted sock Klein bottle. So there's 3 structurally different Klein bottles. Those Klein bottles are much less well known to the audience. I use 2 different background colors, yellow and blue, for arbitrary reasons. And they essentially indicate that you can cut the surface in such a way that these 2 parts, the yellow part and the blue parts, individually are Mobius bands. So a blue right twisting Mobius band and a yellow right twisting Mobius band make the right twisting Klein bottle with the figure 8 profile. Okay. And 2 left twisting bands make a left twisting Klein bottle. Any Klein bottle can always be split into 2 Mobius bands. And here it's demonstrated for the inverted sock Klein bottle. This one we can just cleave in the mirror plane, get the 2 halves. The bottom half here is the right twisting Mobius band. And the left lifting Mobius band on top has been flipped over here so to open up the bottle. And you can see when you kind of lift this thing out from its self-intersection and kind of flatten it out, it essentially is a perfectly good Mobius band. To remember that fact, I would like to leave you with this limerick. A mathematician named Klein thought Mobius bands are divine. Said he, if you glue the edges of 2, you get a weird bottle like mine. So, Klein bottles are made from 2 Mobius bands. Well, I told you before that the boy cap is a Mobius band. So, we can make a Klein bottle by gluing 2 Mobius bands together. Okay? And you see it looks differently again. Okay? Now, we don't have to introduce any new self-intersection. We don't have to stick any hose through a sidewall because the boy cap itself already brings the necessary self-intersections. There is no Klein bottle in 3D that does not have any self-intersections. Unfortunately for that, we have to go to 4 dimensions. Now, I told you Mobius bands come in 2 different shapes, 2 different mirror images. So here's a left-handed and a right-handed Mobius band, left-handed or right-handed boy cap. And we can stick those 2 together. And of course that also makes a Klein bottle. And at the bottom, I show you what I really have to do to make this into a nice sculpture. I first make a gross polyhedral approximation of those 2 shapes, bring them together. Then I apply a subdivision algorithm that gradually makes the facets smaller and smaller and always kind of chops off the edges. And then eventually I cut out the inner parts of all the faces so I get the gridded structure so I can really look inside and see what's going on. And if I send a file like that to a rapid prototyping machine and I wait a couple of days, then I get out a particular shape. And this looks very complicated, but basically it's just a beautifully symmetrically carved Klein bottle, okay? Made from 2 mirrored image boy caps. I put this file into the public domain of my directory, and somebody there found it, and they used a program called Vivid and created this very wonderful, beautiful virtual rendering. So you can have virtual art as well as real physical art. So these boy caps are really handy. Basically, we took 2 of them and we stuck them together and we made a Klein bottle. Okay? Now, the boy caps are also the building blocks of arbitrarily complex single-sided surfaces. So if you want to make a single-sided surface of genus H. Okay? That would be like a bagel, you know, but with H holes. Okay? Sphere is of genus 0, has no holes, no tunnels. A donut is of genus 1, has, you know, essentially one handle or sort of one hole through it. Okay? And the more hole you drill, the higher it goes as a genus. But all of these are essentially two-sided surfaces. But we can do the same tricks with kind of Mobius bands, Klein bottles, and the like. Okay? And the trick is we start with a sphere. If we want to have genus H, we drill H holes into it. And then we take H of these cross caps or buoy caps, stick them onto the holes. And voila, you have the surface that you want. So it's a very handy component. So for instance, if you want to make a genus 4 surface, we take a sphere, we drill 4 holes in nice tetrahedral fashion, we stick 4 of those buoy's cap on there, and we have built ourselves a genus 4 non-oriented single-sided surface. Okay. And of course we can do it with 8. Okay. And so here what I've done is taken a sphere, I essentially put 8 buoy's caps onto that thing in octahedral fashion. And again, I went through a subdivision surface, I cut out the middle part of the faces, and the end result is this nice little sculptures, which took several days to make on one of our faster rapid prototyping machines. Okay. If you can still take it, I would like to conclude with a brief journey to higher dimensions. Okay? For that, let's go back though and start again with what I showed you at the beginning of my talk. These are the 5 platonic solids. They're the only completely regular polyhedra that exist in 5-dimensional space. And regular means that all the vertices are indistinguishable from one another, all the edges are the same, all the faces are the same. Let's actually step back to 2 dimensions, and what's the situation there? Well, all the regular polygons are essentially the regular objects in 2 dimensions, and there are infinitely many of them. Okay? N-gons can go to 17 gon, 215 gon, a trillion gon, you like it. They're all perfectly regular if their vertices are equally spaced on a circle. So why are there only 5 platonic solids? Well, the first thing you have to notice is that the platonic solids are essentially composed out of the regular 2-dimensional n-gons. All the faces of these platonic solids are regular n-gons. Right? There are infinitely many of these regular n-gons, so could we make infinitely many platonic solids? No, not really. Because it's really only the triangles, the squares, and the pentagons that work. The other ones are essentially too round. And what we need to do is we need to bring at least 3 of these faces together to form some kind of a 3D corner. And we can do this with either 3 triangles, we get the tetrahedron, 4 triangles, we get the octahedron, 5 triangles, we get the icosahedron. Or we can do it with 3 squares, we get the cube. If we take 4 squares, you get essentially kitchen floor tiling, okay? Not a 3-dimensional object. Or we can take 3 pentagons and get the dodecahedron, or the symbol for the universe. Okay, now I'm really going to stretch your mind. Let's now use these 3-dimensional cells as the surface element of a 4-dimensional structure. Okay? Just like the polygons were 2-dimensional elements that form the surface of a 3-dimensional structure. We now take these 3-dimensional cells, make them essentially a crust of a 4-dimensional object. Okay? So we use the same constructive approach. We essentially say, how many of these platonic solids can we fit around an edge, and then warp it so it closes up into essentially a 4-dimensional corner? And I will spare you all the details. I just tell you, there's only 6 ways we can do that. Okay? And all 6 of the possible 4-dimensional polytopes are listed in this particular table. So basically, the first 4, you can see in images here on the very left, is of the simplex. It's like the tetrahedron in 4 dimension. It consists of 5 points. What I'm showing you here, of course, are projections from 4-dimensional space down to 3 dimensions. Actually, all the way projected down to 2 dimensions, right? But when I show you a 3-dimensional object here on the screen, your brain knows what to do with it. You can recompose that shape and see it as a 3-dimensional shape. It's a little harder with 4 dimensions, but we do the same thing. We just take points in 4 dimensions, we project it down to 3 dimensions, and then we can make a model. That gives us some idea what these things look like. Okay? So in 4 dimensions, we have the 5 vertices here, including the one in the middle, And in 4 dimensions, all of those 5 vertices are equally spaced from one another. Okay? We cannot do that in 3 dimensions, okay? But in 4 dimensions, we can do that. Now, where's number 5? Well, here's number 5. It actually has 120 cells. Each cell is one of those dodecahedra, which the Greeks thought was the universe. So this is like, you know, what is this? The super universe. It has 600 vertices, 1200 edges, 720 faces. And a model was built on one of our 3D printers. And last but not least, there's the 600 cell that was essentially built from, I think, drinking straws by David Richter here. It's a real physical model that he built essentially on the lawn of his garden. Okay, well, you know, I mean, we can continue that game. Now we have these 6 4-dimensional objects, right? So we can make a 5-dimensional object by using them as the surface elements, right? And then we can go on and on and on. And you think, oh my God, there must be a whole zoo out of there of things. Interestingly enough, from dimension 5 on, it doesn't get that bad. It's just 3 regular polytope for each dimension as we're going it. There's always the simplex. The simplex basically is, in dimension D, you take D plus 1 points, and you space them in such a way that every one is exactly the same distance from every other one. So every pairwise distance is the same, right? And essentially connect them up, and that makes a simplex. Then there are the hypercubes, or the measure polytopes, and they're basically like cubes in higher dimensions. The cube is what you would use in 3-dimensional space to essentially measure the volumes. As, you know, how many volumes, you know, can I do to fill this particular space? Well, these measure polytopes do the same thing in 4, 5, 6, 7 in the corresponding higher dimensions. And then the octahedron is the dual of the cube. Okay, wherever the cube has a face, the octahedron has a vertex, and vice versa. And similarly, in all these dimensions, for every one of these measure polytopes, there's also a dual, and that's typically called the orthoplex. So, you know, since it gets kind of, we're lucky that we live, you know, in 3 dimensions where it's really interesting. 4 dimension would be good too. After that, it's kind of boring. But that's not interesting enough yet. So let's do something even more special. Okay? Let's allow to have polyhedral faces to intersect each other. Okay? Or maybe even have the face itself be intersecting. So this would be just a pentagonal star face. Okay? Can we make polyhedra out of these kind of faces? And indeed we can. And our good friend Kepler, whom we have encountered earlier, has already done that. Okay? So here are the 4 Kepler-Poisson solids. And they essentially have intersecting faces, and 2 of them actually have these kind of pentagram faces. Okay? We can do the same thing in 4 dimensions, and if you do that, it turns out there are 10 such objects in 4-dimensional space. So there might be plenty of good, intriguing geometrical sculptures we can get from that. But we're going to go even more wild. Okay? Well, we've heard about polytopes, and then we heard about Mobius bands and Klein bottles, and the new thing there was that they had single-sided surfaces. So can we make single-sided polytopes in 4 dimensions? And yes, we can. We can essentially build something that's almost like a Klein bottle, okay, and makes a perfectly good polyhedron in 4-dimensional space. Okay? The simplest one of those is called the hemicube. Okay? So what we do is, looks like a cube, right, on the left, but it's only the front half of the cube. The back half we trimmed away. Okay? So there's kind of the gaping hole there in the back, and there's kind of this open equator going around ABC, ABC. Right? And now we simply declare, connect B with B and A with A and C with C. Make them the same points. Okay? Well, that clearly warps things up, but it gives you sort of a diagram that looks like that. Right? That's the connectivity that we really want, because A is the same thing there, and you know, there's exactly, you know, one of each one of those 4 vertices. And so then, when you try to actually make a model, you can make this particular model here. And you can actually make a physical model. So this would be the physical model of what's called a hemicube. The cube has 6 square faces. This one has only 3 square faces, but the square faces now are are not flat, they're really sort of warped into this tetrahedral shape, and three of them are stuck together, properly connected. And if you think about it, or you run your finger carefully along it, you can see it's a single-sided. You can go there and then around the corner. Before you know it, you're inside on the other side. Okay. We actually can do that with all the Platonic solids. Well, not all, but we can definitely do it with the hemi-icosahedron. Same thing. You look at that, it's like the diagram of a half an icosahedron. It's the front half, always the 10 triangles. The 10 triangles have been chopped away in the back. We leave a big gaping hole there. We have this equator. We again label opposite vertices, and we just say, you must connect. And of course, that really squeezes things together, warps them up, and we can again make a self-intersecting kind of shape that looks like the one that you see up on the right. So this is like an octahedron, but kind of slightly warped, so that the three lines through the middle don't coincide and give you the false impression there may be a vertex there. And now comes a really big step, because I'm now going to take 11 of those cells and make a 10-dimensional jewel. Okay, and that's the crowning final achievement of this talk. Okay. So what have we got? We have this object, right? How many faces does it have? It has 10 faces. Right? All right. We're going to take 11 of those objects. Okay. Every one of these objects is going to touch all the other 10 objects, okay, through one of the triangular faces. Okay. It all adds up, right? Every one of them has 10 other ones that it needs to touch through one of its 10 triangles. Okay, that's the plan. How are we going to do it? Well, it takes some doing, but some mathematicians back at Coxeter in Canada, some 30, 40 years ago, already kind of figured out how this can be done. And it gives essentially this color plan, which is, each one of them is one of the cells, and it labels the vertices, but also with the color coding, essentially it kind of shows with which other object it connects in what way. Now, we want to make a model of that, okay? Not just have the abstract description that often mathematicians are quite happy with. So we start with this tetrahedral cell, with sort of 4 faces. And then we add new cells, some of them, with sticks up on the inside. And of course, in order to do that in 3-dimensional space, we cannot just tack things on the outside. Everything has to warp through one another and connect from the inside and be twisted in weird ways. So in the end, it really amounts to, we have 11 vertices that in 10-dimensional space, they can be perfectly on a 10-dimensional sphere, so everybody is equal distance from everybody else, right? In 3-dimensional space, we try to find a way of making them as uniformly spaced as possible, because we never really succeed. Yeah? We can try to put these 10 vertices, say 6 of them on the edges of an octahedron, 4 of them on a nested tetrahedron, and then connect that. Whatever we do, it's going to be a highly confusing and intersecting mess. 6 more cells, it looks like that. We say, okay, this is now the complete thing. Let's try to render it. Well, if you render it with solid faces, you don't see all that much, because a lot of stuff is hidden and going inside. So we say, okay, let's try to make it like semi-transparent. Semi-transparent would be on the right. That's not very good. So I go back to my old trick and says, let's cut out most of the faces. So when you look at, say, the yellow face here, you only see a small sliver of a triangle outlining that thing, and most of it is missing. But that gives us a chance of looking inside and seeing all the edges diving through one another. So this is the full 11 cell. Okay? And it can only really exist perfectly symmetrical where it shows all its symmetries. And that's 660 automorphisms, or 660 ways that you can twist or turn this object and it falls straight back onto itself. Okay? But this only happens in 10 dimensions. Well, 10 dimensions, to me, it rings a bell. Some of the string theoreticians in theoretical physics, they think that our universe actually has 10 dimensions. Okay? 6 of them are really, really curled up very, very tightly, so you can never sort of get there. Okay? But who knows, maybe this wonderful 10-dimensional jewel, this 11 cell, is kind of a building block of the 10-dimensional universe way down there at the Planck level. Thank you for your attention.
If your mind's not
Yeah, so I put the talk up here. Okay, so if you want to go back and look at some of the pictures and say, what the heck did he talk about? You know, then you can kind of find it here.
And we'll also have the video on our website.
Good. And feel free to come and look at, okay, you already know, do 2 buoyant caps make a Klein bottle. Okay. This is a figure 8 kind of twisted Klein bottle, but it's actually one that has been wrapped up into a trefoil. Here is sort of like almost an ordinary Klein bottle, except it's a double sock. It's a pair sock Klein bottle. Here one again is almost an ordinary Klein bottle, but I stuck 3 of them together and make a trefoil. So all of these are sort of Klein bottles. Okay. You know about this one. This was a simple model of the Henny cube, the simplest kind of polyhedral object that is kind of single-sided. Okay. This one is the model for the structure you can find in Sutardja Dai Hall. Oh, I forgot about this one. I should have talked about this, because this is called the music of the spheres. And being that many of you are interested in astronomy, you know that the old image of the universe was kind of a big crystal sphere on which you had smaller crystal spheres that kind of roll around, and on them are maybe smaller yet, and the planets are attached to those. So this is something that Brent Collins carved on about that size. And then we got a commission to also create one of these as a bronze sculpture for the outside of the Missouri Western State University. It's called Music of the Spheres because the ribbon basically travels on the outside of a big crystal sphere, and then there are 3 smaller crystal spheres interspersed, and it kind of loops around each one of them. And in doing so, it forms another trefoil knot. So as far as knots go, it's basically the same knot as this one here. Here's one of the old, very early Brent Collins kind of maquettes, you know, some of these twisted toroids. And then a couple of things I did not talk about. The Arabic icosahedron, if you look closely, it has 20 little trefoil knots all intertwined and essentially forming this kind of, you know, Arabic kind of pattern that you might find in door screens or something like that. And then this is another sort of minimal surface, okay, 2-sided, because we put 2 different patinas on there. I call this a volution shell, and you know, I made a whole series of them, starting with very few holes and gradually getting more and more holes. This was done by Steve Ramuth, another collaborator. He has a bronze foundry in Eugene, Oregon. He's a wonderful craftsman, and he does outstanding work with bronze and patinas. So please come and enjoy the craftsmanship on this smaller sample. I couldn't, you know, bring the more big ones. Questions?
I have a question.
Yes.
So I'm curious, you talked about the conception of some of these sculptures, how they start on the computer, and you talked a little bit about how they're actually built in terms of kind of applying all the different techniques that you're using, actual physical techniques. But I'm curious, when you're actually sort of putting these things together in the computer, how much are you kind of thinking of the limitations of the materials that you're going to use to make them? Will something hold together, you know, if you hang it from, if it's going to be 10 feet across and you hang it from the
Absolutely. I mean, I need to think a little bit about the material already when I'm at that level. And for instance, the 3D printer from Zincorp, basically, it lays down a layer of plaster powder and then selectively dribbles, you know, some binder in there like Elmer's glue or something. Okay? And that's relatively brittle. So you couldn't make a structure like that. It would immediately break apart. You would have to make the struts much thicker. These were mostly done on what's called a fused deposition modeling machine. That one has a heated nozzle that spews out a little bead of semi-liquid ABS plastic. It comes out like toothpaste. Okay. The computer takes your model, it slices it, it figures out the level 17, that's the shape I want, and then the nozzle is guided back and forth at X and Y, essentially painting in that whole layer. When you're done, stage goes down a hundredths of an inch, calculates the next layer, and then crosswise paints that one in. This one gives you something that has pretty much the strength of normal ABS plastic, so you can make much finer structures with that one. Then you go to something big. Now, I think the material becomes a real issue. And in particular, on the first sculpture that we did of this kind, which again was a wood sculpture by Brent Collins that then got scaled up, and it's called Pax Mundi. It's a bronze sculpture that stands in the backyard of the H&R Block building in Kansas City. And it's a simpler version of that. It's basically a sphere with an undulating path that goes around and loops up and down about 4 times. And we had to kind of scale it up, you know, at the same time we have to make it a little bit thinner than what you have in wood, because of course it's metal, keep the price down, keep the weight down. But then something really sad happened is that as we first had it completed together, suddenly it was no longer circular because it was very springy. And under its own weight, it sagged by about 15%. And it's totally my fault not having thought about that. You know, I had a plastic model, I knew it was springy, but it never occurred to me that, you know, the bigger one, you know, strength and weight do not scale the same way when you go up in dimension, right? Weight goes up to the 3rd dimension, strength onto the 2nd dimension, big loss. Now, that would have been a big boo-boo, but Steve Reimers, my hero in Eugene, Oregon, before he even called me and says, Carlo, you screwed up. What he did is he took that sculpture, he hung it from the ceiling at the upper end, okay? And it stretched by 15% under its own weight. Then he cut into 4 of the ribbons halfway through, and it stretched some more. He put in some bronze filler, essentially locked in an artificial stretch state of 15%. And then when he took off the hook and sort of powered it from below, it settled from an oblong ellipsoid back into a perfect sphere. And then he called me and says, I had a little problem. I would like to work with him. So this time I was very much aware of it. You know, I called a program that actually, you know, does exactly the simulation of how much things change in gravity. I simulated the old sculpture just to get the bearing, and it says, it will shrink by 15%. I says, okay. I ran this one through it, and it says it will shrink by 2%. Okay? And that's fine. In addition, though, Steve Reimers, maybe having been burned by the other one, he didn't want to take a chance. So he actually took all the upper big ribbon on the outside and made them hollow to reduce the weight and not lose much strength. The bottom part and some of the inner parts he made solid because you know, they had to be solid for strength, or because they were too narrow. That only cost him an extra 3 months. So I mean, in a way, he bought himself in a way more trouble than necessary. But yeah, ever since, this is very much on my mind. When I had this, I had it as a bronze sculpture. It was much thinner. When I wanted to make this in stone, then obviously, you know, you cannot do a shape that you could do in metal. So I had to artificially really thicken all the flanges. And so they're now good solid 2 inches thick. So again, thinking stone, I had to go back in the sculpture generator, change the flanges, give it a bigger thickness. Now, rather than having it round, maybe I cut them off squarely, created a new file, and that's what created that sculpture, with, you know, with full knowledge of what the end product would be. Yes?
Carlo, the snow structure that you made, how that was done by human beings, I take it?
Yeah.
Teaspoons or something? Or
I what?
teaspoons or knives? Or how did you make the plans for all that elaborate?
First of all, I made myself the 3D model, actually 2 of them which I had on tripod. I also made projections from both sides on a big plastic sheet, which I laid out in my living room and on my knees, you know, scaled up a computer drawing, which we hung over the block in order to get some markings. But then we basically had big ice saws. On day 1, I took that block and I essentially cut a diagonal slab that was 2 feet thick out of it. I think the whole block weighs about 10 tons. On day 1, we probably removed 8 metric tons. So it was back-breaking work, just cutting big chunks of things away to make that big slab. On day 2, we drilled a hole through the center, and you know, with sort of a stick and a knife on a string, you know, we basically made ourselves a big toroidal shape. Okay? So on day 2, we started to convert that into a torus. There, we mostly had pickaxes and shovels, but also ice fishing drills. You know, in Minnesota, they have these 4-inch drills, 2 big holes. So we would drill a few holes perforation, and we could knock away a whole block or something like that. Then, as we got to the refinement phase, we not only had smaller, shovels and scalpels, but we also had a board with a solid grip on it that had some of the tough metal screens that you find in some of the ski resorts and the steps that go up to the the ski lifts, right? And they make perfect rasps. So you take that and you go rasping that thing. So there was a variety of tools that we built specifically for this kind of technique. And there are typically about 15 teams in the snow sculpting competition. And this was our first year. We didn't have the best tools, but we learned, and the following years became these better tools. And so it's an interesting art all in itself. It's not ice sculpting, it's really hard-pressed snow. The way they do it, they build a crate, they fill in about 2 feet of snow, and then the citizens of Breckenridge go in there, just like they stomp the snow down, and then 2 hours later there's another 2 feet of snow, and they go in there and they stomp again until they're up at the 12-foot level, and then they let it sit there for a week, and then 2 days before the event they remove the wood scaffolding around, and there's your heavy block of packed snow, like avalanche snow. It's not ice.
So did it collapse because they didn't sculpt well enough?
No, it collapsed because it was a relatively fragile structure, and we had to actually, the sun was so strong, during building we already protected it sometimes by putting up essentially shadow sails in order to prevent it. But I think what's really bad is that the sun was just reflecting off the bottom layer into the bottom part. Now the whole sculpture, in my estimate, is still probably about a metric ton or a half, and it's resting on 2 pieces of snow flanges that are 4 inches wide and about 1.5 to 2 feet long. Okay? So there's a lot of pressure there. And I think that just structurally gave way when it got too warm. I was like 3 months after the event where I got another photograph for somebody who thought he had just shot the sculpture before it collapsed. Actually, he had shot it probably about a half a second into the collapse. And what you can see is sort of a crack down the middle, and the middle piece there is like 4 inches below, just floating, just got out of location. I mean, for an engineer, it was an incredible opportunity to actually see the onset of collapse of the sculpture. Yes?
I understand that a lot of people in biology now have focused, instead of on the human genome, they focus on protein folding as being the bleeding edge of research. And I wonder if what you're doing has any overlap in what they're trying to do there. Like, for instance, I'm thinking about the affinities of amino acids, which might be even your color coding and folding. But the protein folds in biology don't appear to me at least be beautiful and symmetric and to be like a looping process mathematically. So just talk about that.
So it's indeed a very active research area, and I'm not working in it myself. I have good friends and colleagues that work in it, and it's a very tough problem. But we're slowly getting there. You're given an arbitrary complex formula, and we have programs that with high probability will actually tell you how this particular molecule would fold up and what the final 3-dimensional structure is. A lot of it, originally it was mostly clever chemists that figured out locally what's going on and program that calculated the electrostatic potential and then tried to optimize it, and it's a humongous amount of calculation. More recently, I think, the winning technique is machine learning, as in so many other domains. Basically just say, show me 10,000 molecules, show me the formula, and show me what the end result is. And I just look for common patterns, okay? And with that kind of thrown into the hopper as well, they're now getting pretty darn good of predicting kind of what shapes and what would happen. As you say, they're normally very organic-looking conglomerate things, and I like more symmetrical, open structures. So there's not that much potential that I see to directly, take that and inspire any kind of sculptures. So I have not paid all that much interest exactly what shapes come out there and what they're doing.
Any other questions?
Yes.
Are your computer programs available?
Yes, the sculpture generator is online. If you go to my homepage, and I think you have to add the /GEN, you get to a page that guides you there. You can download it. Many people have downloaded it, and some of them have sent me photographs. Says, "Oh, look at my earrings from my life, and they get me here and all stuff." So a lot of people have done neat stuff. One thing I observe, if a beginner kind of takes the sculpture generator, they typically overdo it in complexity. They kind of move all the sliders to the right. Okay, we take 17th order saddles, and 15 in a row, and we warp it, 300 times. And the shapes typically start to look like, you know, the cooling tower in a power plant, not like a sculpture, okay? And then as they mature, they get restrained and they go back and, you know, make it simpler. I once had Helaman Ferguson have a go at the sculpture generator. He's a stone sculptor, and you may have seen his stone sculpture up at the Mathematical Science Research Institute, which celebrates the Klein quartic surface, which is 24 heptagons. It's kind of a nice marble sculpture, and it's kind of a seven-sided pedestal coming out of a Poincare tessellation. So he immediately thought stone, right? So it's like he had all of this in his mind when he used a sculpture generator. And he basically used a single saddle, okay, which had never occurred to me. I mean, just take a single saddle, but stretch it really long, and it's just the simplest possible saddle. So, you know, you have two legs sticking up, two legs sticking down. And then warp this around so that they join, so you have to give it a 90-degree twist. Right? And it really looked like a beautiful little stone sculpture. Basically, it was two twisted stone rings that kind of joined in a single saddle. So, yeah, many people have used it at different scales for different purposes, and that one on any Windows machine, unfortunately, only particularly old Windows machine, you just take the executable, dump it in there, you hit the exec button, and it comes up, and it's self-explanatory. You just move those sliders, and you get interesting shapes. Yes.
You mentioned a work on the 6th floor of what building on the campus?
Okay, Sutardja Dai Hall is that new brown building that's between Corey and the old Naval Architecture School. If you go into the lobby, you have to take the elevator to the 6th floor, and then exits on the back side. It's on the south side against Davies Hall, or you can go from Davies Hall to the 6th floor. And on that terrace is where you find this. Yeah, on the terrace it stands up there. We call it the Tower of Engineering. And so on. Also, if you go to my webpage, there's a little story there. You find this picture, you click on it, and you get the story, and you see some pictures from the installation day a year and a half ago. More questions? Yes?
So, thank you so much for this fascinating talk, and I'm just wondering, do we now know which came first, science or art? Does it matter?
I think you can make up your own mind, as I truly think that the thinking is actually so much overlapping that I think they have co-evolved. Right? I mean, it depends many what is science, but just to make fire and control it, I think that's already science, because you don't really know what you're doing and observe it, and you know what materials burn and all of that. Right? And so, you know, this goes really back, and I think science in that sense goes much further back than mathematics, which is a more abstract construct. So I think the thinking needed for science and art are much more related and maybe have the same origins.
It's so integrated.
Yeah. But that's just my opinion. I thought it was a fascinating thing to think about, and by all means you're invited to think about it.
So check out the sculptures. Come back on December 21st to hear Professor John Taylor talking about fungi, and let's thank Professor